This video explains the importance of measuring diagnostic ability by using misses, hits, and false alarms as opposed to single metrics such as percent correct or the figure of merit. We illustrate the concepts with an example to measure the diagnostic ability of a model that simulates deforestation along the Trans-Amazonian Highway. The gray in the middle map shows the spatial extent, which consists of government-imposed rectangles extending perpendicular to the highway that traverses from east to west. The irregular white patches in the east have no data due to clouds. The map on the right shows the reference data, which we use to indicate the truth, where black indicates forest loss and gray indicates forest persistence from the start of the simulation to the year 1999. The behavioral landscape model has a variety of parameters to simulate deforestation. Each combination of parameters influences the quantity and spatial allocation of deforestation. These are output maps from 3 model runs, each with a different combination of parameters. The quantity of deforestation is 15% in the output on the left, 24% in the middle, and 49% on the map on the right. We overlay the reference map with each of the simulated maps, which produces one of 4 possibilities for each pixel. A miss is where the reference map shows change and the simulation map shows persistence. A hit is where the reference map and the simulation map both show change. A false alarm is where the reference map shows persistence and the simulation map shows change. A correct rejection is where the reference map and the simulation map both show persistence. Correct rejections and hits are agreement between reference and simulation. Misses and false alarms are disagreement between reference and simulation. False alarms are fewer than misses if and only if the simulated change is less than the reference change, as the left map shows. False alarms are more than misses if and only if the simulated change is greater than the reference change, as the right map shows. The Venn diagram has 2 sets, reference change on the left and simulated change on the right. The sizes of the sets are not necessarily equal. The intersection of the 2 sets are hits. Misses are reference change and simulated persistence. False alarms are reference persistence and simulated change. Correct rejections are neither reference nor simulated change. Correct rejections are irrelevant when the size of the extent is arbitrary. In these cases, the percent correct is also irrelevant because percent correct combines the sizes of hits and correct rejections. This slide shows results for 18 runs of the simulation model. Each stacked bar corresponds to 1 run. The sequence of runs along the horizontal axis are in order from least simulated change on the left to most simulated change on the right. Each stacked bar is a Venn diagram, with the reference change as the set on the bottom and the simulated change as the set on the top. The sum of misses and hits is the size of reference change, which is 26% of the study area. This format of presentation compares the various model runs clearly because it shows the sizes of misses, hits, and false alarms. Run number 8 is the run for which the size of simulated change is closest to the size of reference change, which the graphic shows because the size of misses is the closest to the size of false alarms. The graphic shows that the size of simulated change is less than the reference change for runs 1 through 7, as false alarms are smaller than misses. The graphic also shows the size of simulated change is greater than the reference change for runs 9 through 18, as false alarms are greater than misses. The figure of merit is a summary metric computed as the ratio of hits in the numerator and the sum of misses, hits, and false alarms in the denominator. The figure of merit is 0 when there is no intersection between reference change and simulated change, and 100% when there is perfect intersection. The figure of merit ranges from 27% to 35% among the 18 model runs. It can be helpful when it is essential to have a single metric to compare the model runs. However, the graphic illustrates how it fails to show important differences among the model runs. The figure of merit fails to show the size of misses compared to the size of false alarms, thus fails to show whether the model simulated more or less than the quantity of reference change. Regardless of the metric to measure diagnostic ability, it is helpful to compare a diagnosis from a simulation model to a diagnosis from a naive model. A naive model portrays the diagnosis that derives from a simplistic description that is easy to understand. For our case study, we created a naive model that allocates the simulated deforestation as close to the highway as possible, thus we call it the highway allocation. This reference map shows the highway through the middle of the spatial extent. We created 18 highway allocations to correspond to each of the 18 runs of the behavioral landscape model. Each highway allocation has the same quantity of simulated change as one of the runs of the behavioral landscape model. This graphic gives a pairwise comparison between each run of the behavioral landscape model, shown as a blue dot, and the corresponding run of the highway allocation, shown as the corresponding red triangle. The vertical axis is the percent agreement between the reference change and the simulated change. The horizontal axis is the percent of simulated change in the spatial extent. For each of the simulations, the red triangle of highway allocation is directly above the corresponding run of the behavioral landscape model, meaning that the highway allocation is more accurate than the corresponding run of the behavioral landscape model in terms of agreement, number of hits, and figure of merit. Other summary metrics could reach different conclusions. For example, simply looking at the map shows that the spatial patterns in the behavioral landscape model match the pattern of deforestation along the roads perpendicular to the highway better than the highway model would portray. This graphic shows also some alternative naive models. The dotted line shows the percent correct of a uniform allocation as a decreasing function of the simulated quantity. Thus, the behavioral landscape model and highway allocations are both more accurate than a uniform allocation. The dashed line shows the percent correct of a naive model that shows zero deforestation. The reference map has 26% deforestation. Thus, a naive model that simulated zero deforestation would be 74% correct. The solid lines show the maximum and minimum bounds on the percent agreement given the size of simulated change. The most important takeaways are that researchers should express diagnostic power by reporting the size of misses, hits, and false alarms. Correct rejections are frequently irrelevant and misleading, especially for cases when the extent is arbitrary. Percent correct can be misleading because percent correct combines hits with correct rejections. If it is essential to use a summary metric to compare across cases, then the figure of merit can be helpful. However, the figure of merit fails to show crucial information such as whether the size of misses or false alarms are larger. Researchers should compare any diagnosis to a naive model that relates to a certain research question. More videos related to the topics covered in this video are available at the link at the top of the page. Professors Pontius and Walker published this research with their students in 2007. For methods that involve more than 2 categories, see the 2019 publication by Varga et al. We thank the United States National Science Foundation and NASA who supported this research.